Hello student, welcome to today's session. So today we will be discussing one important topic of inorganic chemistry in regard to borate. In fact, this particular session, why I have written it as mind-blowing discussion, because after the session you will feel literally very strengthened and you start loving inorganic chemistry. So why I'm placing this session today is because of the fact that last time or 2-3 days back I uploaded this particular session where I talked about boron compounds. There I asked a few questions. How many water molecule of water of hydration are there in the following compounds in borax, calaminite and things like that. And also I have asked, I think so, that what can be the monomeric unit for the calaminite. So to address these questions, so I am thinking of placing one more session on to the topic of borate. So this particular session would be very important those who are preparing for IIT Advanced this year, or for chemistry Olympiad, or anyone who is having love for chemistry. And love for chemistry, in fact, I just want to break that apprehension. Those who are little apprehensive about the topic of inorganic chemistry, I would with these videos, my endeavor would be to create passion and love for inorganic chemistry. And those who are preparing for NEET examination, just look for the chemical bonding aspect, which I'm going to show in today's lecture in terms of the borates. So let's go directly into the topic. When I talk of borates are basically boron containing oxyanions. Any anion which is containing boron along with oxygen, we can refer that to as borates. Just like shown here, they can be of two types. Either they can be monomeric, where one unit is available, just like in orthoborate. First one is orthoborate, second one is metaborate, and it can be polymeric. So we would be discussing all of this in detail. When it start becoming polymeric, it can be either in the form of linear or in the cyclic rings. Beautiful, just like the silicates. Do see into the session of silicates as well, uploaded few days back. So when I talk of borates, there are two ways of classifying it. Borates can be available in nature in two forms. One is the anhydrous form. When I talk of anhydrous form, simply I'm saying that like orthoborate or metaborate, something like this, or B4O7 2 negative, or B6O11 4 negative. In anhydrous form, when I am talking these to be in present in anhydrous form, most of the time they would be, this is an important tip to remember, the boron would be available because it is being joined to the oxygen, because in just like in these cases it can become polymeric. So in them the boron would be in a triangular planar form, where this unit is available, or it is present in this form of unit. Or other way around, you can also think it like this, that one of the boron, it can be in this form also. One of the oxygen carries a negative charge, other two oxygen are single bondedly attached to the next boron, something like that. But the triangular planar form is there in the anhydrous form. When you talk of hydrated one, when I talk of hydrated borates, just like if I just would write something in terms of B4O5 OH4, just like this one, this is the anion of hydrated anion of borax itself, and it is 2 negative, something like that if it is present. Or B6O8 OH6, this is of that of calaminite. In these, what you are able to see here, a MCQ question can be asked, or something in regard to this can be asked. Here the boron units either would be in the form of trigonal planar, or must be having a tetrahedral unit as well. It definitely would have a tetrahedral unit as well, something related, something bonded here, and as a consequence this boron would get a negative charge. So it is in the tetrahedral unit also, B4 something like this, further joined to something else, and trigonal planar as well. And as a matter of fact, do also remember this trick or tip, that whatever in the hydrated borate, whatever is the charge on to the total anion, if the charge is 2 negative, there must be, out of this 4 boron, there must be 2 borons in the tetrahedral form. whenever the boron is in the tetrahedral form in a oxyanion, that particular boron is going to get the negative charge. This is first you always have to remember. And say for example in this there is B6 and the charge is 4 negative, so there must be 4 borons which are in this form. So this is very important to remember. And the another classification of borates is borates can be classified like this: monoborate. Just like if you have only one, it is the anion is present in such a way that it contains only one boron atom. So it can be orthoborate or metaborate. It can be diborate like just B2O5 4 negative or 2 negative, or triborate. Triborate can be B3O6. This is a very important one. Tetraborate, we talked about the borax, anion of the borax. And pentaborate can be B5. This also is a very important anion. And hexaborate is B6 O11 4 negative, that is of the Calaminite. So depending upon how many boron atoms are there in the anion, it can be diborate, triborate, tetraborate, pentaborate. Make it a point, I just have wrote few of them. The list is very long, but these I find is very important from the point of view of +2 examination or competition exams for the IIT or JEE mains or NEET examination. Otherwise the list is very lengthy, so because it can exist in many polymeric form. So now coming on to the discussion of all of this, we can go in little detail and we'll do the things a little speedily so that you would feel comfortable with. So coming on to the first one, when I talk of first one, anhydrous borate, we are starting with anhydrous borate and we'll see in the anhydrous borate, monoborate, diborate, triborate, pentaborate and hexaborate. Till hexaborate we can go. Otherwise borate can go till B10, O21, something like that. So it can have number of other borates as well. But after doing this much number of discussion, if in case some entity comes in the exam, you are able, you would have a skill set then to solve it in the paper as well. But if you do not have any idea, then it would be very difficult to identify the structure. Now coming on to the first one, orthoborate is a simple one, which is BO3 negative, and metaborate also is very simple. This we already know in many times in the borax bead test also we have talked about the metaborate. Now coming on to the diborate. So I am picking up one of the example of diborate is, in this case what you can think it like this, that if I want to generate this particular anion, so this particular anion can be generated from these two, borate and metaborate joins. How does it join? A simple reaction. You can do it like this, just like the organic chemistry. This one negative charge attacks it, this moves further. As a consequence, what do you get here is, they can ask you a question based on this as a question to be, how many BOB bonds are there in this particular anion? So it is not very tough, easy. So this is B2O5, and what it would be 4 negative. This particular anion would have 4 negative charge. Is it okay? So this is quite important. Similarly, if I would go for the next one, triborate, this particular anion is also very important. If you just would polymerize metaborate anion, if metaborate anion undergo trimerization, if it undergo trimerization, what simply you would get B3O6 3 negative, as simple as that. So how could we show that? I just, to save time, I have drawn few of the things. If I do it, so just see here, what I can do here is, if negative charge attacks this boron, then this will move further and this would carry a negative charge. That negative charge then attacks this one. So just to make the thing simpler, I just simply have written it like this, that in that sense this bond goes here, and as a sense this bond just goes here and this moves here. As a result, what has happened, 3 entities or 3 moles of metaborate got joined through these green lines, isn't it? This got joined here, here and here. So what entity do you get here is B3 negative, BO2 negative, this trimerizes as thrice. So it tend to give you B3O6 3 negative. So here IIT advanced people may ask you a question where they can mix 2-3 things together, organic, inorganic, something like this. This could be a expected question in upcoming exam. Which of the following species may undergo trimerization under given set of conditions? They will ask you SO3, more than one choice question. They can say it like this: SO3, metaphosphoric acid, formaldehyde, and metaborate. So all of these, the answer to this question is A, B, C, D. All of these can undergo trimerization under a given set of conditions, where organic, inorganic, within the organic, this is the oxygen family, this is the phosphorus, nitrogen family, and this is the boron family, and this is organic part. So the things can be asked in such a way that the examiner would check many things in the paper. Just like if I would show SO3 would join it like this, as simple as that. We already have done many times in inorganic classes. So this bond goes here, this goes here, this goes here, and you would get a structure as being shown here. So it can undergo trimerization, and they will ask you the want-of factor also, that if what would it be, 1/3, something like that. So similarly, and you can go for this one also. This can also undergo trimerization, isn't it? This can also undergo trimerization, and formaldehyde happens to do the trimerization to give you trioxane, which is being shown here, trioxane. And BO2 negative, we already have done it, that it on trimerization can give you a anion of the type this way. So this can be a sort of expected question. Coming on to the main topic. So we already have done triborates. Now coming on to the tetraborates. So as regard to the tetraborate, this is the one of the most important which we come across in the topic of borax, which we did in the last video as well. Let me repeat once again, because this is quite important, quite expected. So this can be formed from, if you would just treat B2O3 with metaborate, you end up getting B4O7 2 negative. Now how does it happen? Simply we did last time borax B test in a reverse way. Now I can show it like this, that if I just would attack this part of the species, this bond goes here and this goes here, as simple as that. And similarly, if I would attack this part here, this bond move here, and you end up getting this. As a consequence, what exactly you have got here is, you got a species negative boron, this got joined here, this got joined here, and between the two borons there is oxygen. Wow, beautiful it is. And you may go the reverse way also, like in borax B test. In the borax B test, if you could recall, I did it like this, that if you take it this way, this goes here. Are you recalling or not? If I would just take it back, this would go, rather I should show it like this, this will go here, and this would become a negative charge, and on heating this borax decomposes like this. And similarly, if I would take this back, let me show with the green marker only, and if you take this back, this bond goes here and this would come here. So you would get the 2 moles of metaborate B2O3 which appear as borax B test, as simple as that. So coming on to the next one, pentaborate. Pentaborate is B5O8 negative. This again is if this sort of a question comes in the paper, if you haven't done earlier, it would be very difficult to identify the structure of this molecule. And make it one thing more, that make it a point, as I did few of the things like B2O54 negative we did, then we talked about B3O6 3 negative, and then we talked about B4O7 2 negative, something like this we have done. Now make it a point, when as a whole just concentrate on the negative charge. I can say on this, although the negative charge is on the oxygens, because in the anhydrous form, as I said, in the hydrated form the boron would get a negative charge, but in the anhydrous form most of the boron are in most of the anions would carry a negative charge on oxygen. But as a whole you have to remain this way enlightened with that the point here is that if you just would see that in this particular anion, per boron there is one negative charge. Here per boron, you can say it like this, the negative charge got decreased from one negative. It got decreased from that value minus. So if in the total anion, I can say it like this, in the total anion, if per boron the negative charge got decreased from one negative, it get decreased from one negative, then in the making of that structure, B2O3 must be used. B2O3 must be used. Just like see here. Here also I have used B2O3. B2O3, because if I would say here that per boron there is minus 1/2 negative charge. Actually the negative charge is on the oxygens. I'm just making a tip to remember that if in case you would get a different borate than the one I am discussing, then you need to be vigilant about if the total negative charge per boron is greater than 1, then the species which are making them either would be B3 3 negative or metaborate. If it is less than 1 negative, then definitely it would be using B2O3 during its formation, just like the one I'm going to show you in a minute for this particular fine. B5O8, we want to make its structure. How does it look like? Is it okay? So it would look like something like this. If I would just show you, just try to remain with me. How could I show this one? If I would attack onto this one, is it okay? If I would attack onto this one, and in the process, if I would take this here, is it okay? And if I do so and took it this way. Now what exactly I have done here is, I just have attached onto this green boron, I just would take the same color for the ease. So this is the boron which I have attacked, and this had been a green one. This got joined to the boron which is of the red color. Is it okay? And this becomes this, and this got detached from here. Okay, so this got detached from here. Fair enough. Now what I am going to do is that if I would attack this, because this boron can get this negative charge, because you have to keep one negative charge onto the entire molecule. So this is what I am referring to. So this particular anion in specific, here this is the case. As I said, generally in the anhydrous form it is in the planar form, but this particular entity contains boron in one of the boron is in the tetrahedral fashion and would carry a negative charge. So beautiful structure it is, interesting viewpoint, always keep it in mind. So this is a very important anion. If you have done already in the paper, then only you can do it. How they can ask you a question? They can ask you number of BOB bonds in it, or they can simply ask you number of tetrahedral boron atoms, or trigonal planar boron atoms. So these can be the question from the chemical bonding aspect as well. So there are 4. These trigonal planar are 4. Trigonal planar, if you could see here, these are 4 in number, and tetrahedral one is 1 in number. So this is 1, this is 4, total becomes the 5. So it had been an interesting one. Coming on to the hexaborate, which you people asked me, and I asked this question in the last video of boron family. So B6O11, this is Calaminite, and here I am writing the anhydrous first. So it can be, again, if you could see, per boron the negative charge is less than 1 negative. So we definitely would be using B2O3 during its formation. So it would become B6O11 4 negative. Is it fine? 8 and 3 11. Yes, it is perfectly right. Now how do I make it? This is very important to tell you. Now see here what I am going to do. If I would attach this negative charge here, such that this bond moves here, such that this bond moves here, such that this goes here. Beautiful it is. Beautiful. Beautiful. I'm loving it. So are you. And this is going to attack this one. This is going to attack this one. And this is going to attack this one. As a consequence, what exactly did you get? So we are able to receive a molecule of this shape. Let me use the same color so that you can feel it with more curiosity and more interest. So how should I go for its making? So it would look like something like this: B O B O B. So this we have just made. I need to have a space here. Just hold on. So we would be writing something like this: B O B. So this here and this also here. Okay. And thereafter I used this particular color. So this got joined here. This also got joined here, and in between also it got joined here. And what we are left with here, one negative charge here, one negative charge here, one negative, wow, interesting, one negative charge here. So this is the structure of B4O11 6 negative. B4O11, B6O11 4 negative. So here how many BOB bonds you could see? Let me draw it once again for you. So I just have made it like this. This is the structure we just have made. So there is a BOB bond here, and this also would have, for this you people are little confused with. So this is the species which we get. Okay. So this is the entity which we have received. So now if I have to mark how many BOB bonds I have got, so one, and this is one, this is the second one, this is the third one, and similarly 3 on this side, and 1 is this one. So total becomes, BOB bonds become 7 in number. And in the hydrated form, it turns to take some other shape, which is again very interesting. So hope so you have understood it well, that we talked about this particular species last time also, where I haven't answered it you and I said you to do it yourself. So we found that there are 7 BOB bonds in this particular structure. Coming on to the next viewpoint. Now coming on to the hydrated borates, primarily we would be doing 2 or 3 important one which can be asked in IIT Advanced. This in particular is very important, which we talk about borax. So this we did last time as well. So in this this particular anion we just have made, which we call it as anhydrous form. So it was B4O12 2 negative. So this anion we just have made. Now in this particular case, you have to now place, if I just have to add water into it, what question do we get here in this? That this is the 10 mole of water they have given, or 8 mole of, now that would also depend upon the question how they theoretically could ask you in the paper. So you need to be vigilant. So we have to actually, this is the species. For this particular species, we simply would want to make it in such a way that how many water molecules would be used so that octet of all the elements in special boron get complete. What I'm trying to say here is, first one H positive come here and would join to this from the water, and the OH negative of water then would attack this one, so that I could generate a negative charge here. Similarly, one H positive attacks here, and OH negative of water would attack here. So as a consequence of this discussion, that we would see that these two boron would get 1 negative charge. So if they would get, because the counter ion is sodium, so you need to have in totality on that hydrated anion 2 negative charge. Let me repeat once again what I just have said. So I placed H positive here and OH negative onto this, and similarly H positive here and OH negative to this side. So as a result, this becomes negative and this also would become negative. I think I made my point clear. So what we get in this particular case is one OH goes here, OH goes here, and this would turn up to get this particular structure. So in formula form, what we have done, so we wrote B4O5. These 5 are the BOB bonds, and there are 4 OH groups which are creating a 4 negative charge, 2 negative charge. As I told you in the start of the session, that whatever is the amount of charge you would see on a hydrated anion of the borate, that much number of tetrahedral boron atoms are there in this. So you may get question on this discussion in this way, that in this particular anion, how many borons are in tetrahedral form, how many are in trigonal planar form. Now the important one, which is the case of the Calaminite. In the case of Calaminite, we just have made the structure of the B6O11 4 negative. We just have made few minutes back in this. Let me show you once again so that you can feel it with me what I'm saying. So this we have just made, isn't it? This structure we have just made, where we have shown this particular structure. So I wrote the same structure again, so just to save the time. So this is the structure which we have. Again, what basically I have to do, I have to add water into it. Out of 5 water, how many waters would go into it such that it would retain the 4 negative charge? Now this is very important. You generally would not get much of the discussion on this particular thing on books or onto the net. So make it a point, be attentive and listen to me carefully, because there are 2 ways to explain this discussion. Now one way is, I just would place one H positive here. Just remain with me, just like the one we have done for the borax as well. So H positive goes here. So I just would place one OH here, so that this would become negative. Is it okay? Then again I will place one H positive here, one H positive here, and one OH negative here. Is it okay? And then one again H positive here and one OH here. So in totality, how many water molecules did I consume? I already have consumed 3 water molecules. Let me repeat once again, because this is little tricky and interesting. Let me do it once again for you people with this particular structure. What I just have said, that if I will place one H positive here, so this becomes OH, and I just would bring OH here. So as a result, this would become negative. Fine. So one water molecule, if I would write water here, how many water molecules I have used? So I used first water molecule. Now coming on to the next one. Now I am saying place one H positive here, one H positive here. The bond get made here with the H positive, and I just have placed one OH negative here. So here it becomes one negative more. So I used one more water molecule. And similarly, if I would place one H positive here and this one OH here, so I used one more water molecule. So in totality, I am going to see the how many negative charge did I am going to see in this particular case. So the negative charges which I am going to see, one is here, another is here, 2, this is the 3, this is the 4, and this is the no, here you don't have, because this O negative and H positive got joined with. Let me write it once again for you people. So what I did is, so I just have placed one OH here, one OH here, one OH here. These are the 3 OH groups, and these are the 3 H positives. Fair enough. And now let us see into the negative charge. This negative charge was already there. It is still there. Negative, negative, and negative. Now you would ask me what we have made this. If we would count this very carefully, this is B4, sorry, this is B6O. Now let us see into it how many oxygen atoms do we have. 1, 2, 3, 4, 5, 6, 7, and this one is 8. So there are 8 oxygen atoms. And this oxygen atom, or you would want to say it like this also, O7. At this juncture, you are going to tell me like this, O7, because this is between BOB and one oxygen is also there which is carrying a one negative charge. And apart from here you also would see OH6, isn't it? There are 6 OH groups where I would be able to show you 1, 2, 3, 4, 5, 6. There are 6. So in totality you have 6 OH groups. And now the point is, I should rub these dots, otherwise it get confused with the negative charge. So this is 6, and what is the total negative charge do I see? So the total negative charge I'm seeing 1, 2, 3, and this one is 4. So the 4 negative. Now the point here is, I may show you this as this also. This is a very, very important viewpoint to remember, which generally you don't find in major of the books. So O8, OH6, 4 negative. So this oxygen seems like present here as simple O negative. The point is that in the case of Calaminite, this anion in totality, this complete anion get polymerized with another anion on addition of water. What I'm trying to say here is, the next structure you feel little, although I have drawn it, let me show you if you are able to remain with me. So this is the one anion. What is this anion? We just have wrote B6O8 OH6 4 negative, OH6 4 negative. This is the anion which we have just wrote. I'm saying this anion is going to get polymerized with the adjacent anion. In what sense? This negative would complete its octet. This boron would get that negative charge. And similarly, this would attack the next one. As a consequence, what you are able to see here is that a polymeric structure is being generated of this form. A polymeric structure is being generated of this form. So during the polymerization, what I did is, this negative charge attacks onto this boron. So there is a bond here formation. That boron which we have wrote B7O, if you could recall in the previous slide, now turn up to get a form as BOB. It tend to get a BOB form. And because now it keep on repeating it like this. One viewpoint is this. So make it a point. 3 water molecules have been used during this polymerization of 2 anions. Or simply, if somebody would ask you that what we basically have done in this particular case is that I may show you like this: Ca2 B6O8 OH6, and now you have to write it here because you already have used 3 water, so you are left with 2 water. So the water of hydration actually would be 2, if theoretically it could be asked it like this. Another viewpoint is that you would find in many of the books this particular anion written like this. Let me repeat what I'm saying. So I'm saying calcium 2 B6O11 5 water may be shown in the books like this also: B6O8 OH6 2 water. And in many of times you would find in many of the foreign author books, you would find some books are writing this particular anion like this also: B3O4. This is 3 and this is twice. Oh, this is twice. Something like this. Now if I would break it like this, what structure do I get? Ca2 positive. This is very interesting. And this would be 2. What are 2? So 2B, let me show you. It would be B3O4 OH thrice. 2 negative. So this also is a monomeric unit. You can say this is the monomeric unit of Calaminite. Monomeric unit of Calaminite. Or you can say it like this, that this particular unit underwent dimerization, and after dimerization in the three-dimensional structure it further undergo polymerization to give you a polymeric structure of this type. And to show you that thing in more in depth, this particular thing in more in depth, we may think it like this also. While making anhydrous form, this is the anhydrous form, and if I just would turn anhydrous form into hydrated form, what does it mean? Hydrated form means that whatever water, 5 moles of water we have written after the bracket, some water molecule will go into the anhydrous form. So you can do it like this also. This water attacks it, this bond I just have broken if you want to make the monomeric form. So what I did is, one H comes here because and this would change into OH. Am I right or not? Or should I do it in 2 steps? I think I am making sense, isn't it? So this in a way now would show you. So what I did is, or you just would want, let me show you that way also. What I just have done, so I just have attacked it with water. So this would get a positive charge. Now the intramolecular proton shift, this H positive goes here because it is carrying a negative charge. As a result, both of these now would get OH groups. Both of these would get OH groups. Is it okay? Now what we can do is, because the two entities got disjoined, now these got disjoined. Now what I am going to do is, this negative then attacks on, this negative then attacks onto this boron, and this negative attacks onto this boron. As a consequence, you can show it like this. Just feel it with me. You would get 2 such units. I just have attacked O negative onto the boron which is containing OH group, and still the negative charge is 2 negative. Is it okay? So in totality, you have 4, because this also is a negative charge, this also is a negative charge, the total becomes 4 negative. Now thereafter, what we can think it, once you get this, we just have used one water molecule is used, and at maximum we can go for the 3 waters. So what we can do further is this one. So now what I can do is, this one H positive goes here, OH negative goes here. So as a consequence, you would get this structure. So this is the, you would get such 2 structures, and this is the monomeric form of the calaminite. So beautiful it is, interesting it is. Moving ahead, so I think the things have become little engaging, but anyhow, this is very important. So this particular form may have this viewpoint, and this viewpoint I have explained how B6O11, or rather I would say B6O8OH6 can be shown to break down into this form, that again with the help of water itself. Now lastly, we are left with one more, the hydrated form, because this again is a very important. A few minutes back we already have discussed about B5O8 negative, that is this structure. Now in this case, how could you add water into it, because you have 2 moles of water here shown in the paper. So water of hydration shown as 2. Is it actually the water of hydration? Let us check this out. So this water attacks it. If I would attack this water, so this bond goes here and this goes here. And similarly, if I would attack this water molecule, just like in the previous case, this bond goes here and this goes here. As a consequence, what you are able to see here is, what did you get here? You would get something like, here you would get OH, and this would become positive. This bond got made here. Let me change the color of the marker. Let's say, okay. So this becomes O negative. And similarly, on this side also, you just have added water, positive, because this bond get broken. This bond got formed, and this becomes negative. Now what would happen? Intramolecular proton exchange. So in doing intramolecular proton exchange, what would happen? This H positive goes here, and similarly one of the H positive goes here. So I think you are able to get this. See this video little slow by pausing it and just make the structure, and ultimately you would end up getting this particular thing. So in this particular question, they may ask you that how many BOB bonds are there. Number of, again the question would be number of BOB bonds, number of BOB bonds, number of B tetrahedral in this particular anion. What is this anion then would be said as, and one is this, and number of water of hydration, number of water of hydration. So number of water of hydration happens to come out to be 0 in this case, because all the water get consumed up, and this is the counter ion is Na positive, and here you have a negative charge. So number of BOB bonds are 1, 2, 3, 4, 5 and 6, and number of tetrahedral borons are 1, and planar borons are, planar boron atoms are 1, 2, 3, 4. So 4 are the planar boron atoms. So this again had been important question where we talked about NaB5O8 to water happens to turn up to written as NB4. How many are the oxygens? Oxygen had been, so this OH becomes 4, and this had been how many? 1, 2, 3, 4, 5, 6. So 6 are the oxygens here and 4 are the OH. So there is no water of hydration. So hope you enjoyed today's session. We talked about lot many things in regard to the borate. Have a nice day, stay safe, and very soon we will be placing very important topic, inorganic topics in regard to IIT Advanced very soon, uploading very soon. Thanks a lot. Have a nice day, stay safe, and take good care of yourselves.